Example 2. Find the form of y sub p for each equation. A. Y double prime plus 5y equals x squared. B. Y double prime plus 5y equals 180x squared times e to the 5x. C. Y double prime minus 9y equals x e to the x plus sine of 2x. Okay, let's go to part A. Remember, we only care about the right side, so for all of these, let's just x out that left side. Whoops, I accidentally x'd out a little bit of this. But we want to keep that 180, even though it doesn't matter. We still want to keep it. So for part A, all we care about is this x squared. Now, if you remember what I said before, we want to find a form of y sub p such that all of the derivatives of this will be included in it. The way we do that is we just say y sub p equals ax squared plus bx plus c. And I hope that makes sense, because if you can just calculate the derivatives of x squared, it will be 2x and then 2 and then 0. And it's pretty obvious that x squared, 2x, 2, and 0 are all included in this. And in fact, whatever x squared plus x term you have, it would be included in this. And so that's why the form of y sub p is ax squared plus bx plus c. All right, let's go to part B. This is the first time we've seen multiplication yet. The way we deal with multiplication is we just multiply what we would have done for both terms individually. We go y sub p equals ax plus b, because that's what we would have done for x squared. Oh, ax squared plus bx plus c times, and you might be tempted to do something like d e to the 5x, but you actually don't need to do that. You can just write e to the 5x. And that is because if you think a little bit more, if you put a constant in front of that, it could just distribute to these previous terms, and then the constants would kind of all just mesh together. So it's kind of useless to put a constant in front of that. Okay, so that is part B. Now let's go to part C. This is the first time we've dealt with addition. When we do deal with addition, we separate the summed terms and then solve for them separately. So we actually go y sub p1 equals, and then solve for this one, ax plus b times e to the x. And now let's go y sub p2 equals, and let's just write c sine of 2x plus d cosine of 2x. And I hope that these both make sense. The only thing we're adding new here is the fact that we're solving them separately. But we don't need to solve them, we're just writing it in the right form. Okay, so that is our answer for part C. Now, I'm going to try to explain a little more of a logical way of thinking about finding the form of the particular solution. Now, I want you to write this down. You can use this method for, and I wrote this next part down, so I hope my notation is okay. A sub 1 y differentiated n times, that's not y to the n power. So y differentiated n times, I think I might have to go like this. And then plus a2 y differentiated n minus 1 times plus all of those terms until you get to a sub n times y. And then that is just equal to g of x. You can use this method for something like that, the stuff we've been doing, when g of x is a linear combination of finite products of one, a polynomial, two, e to the ax, and three, sine of bx or cosine of bx. Now, what a linear combination means is just a series of multiplying them together and adding them together. So you could really have any combination of these three things added together and multiplied together. Albeit you can only have finite products, so you cannot have infinite products of anything. But you could, like what I had in the previous example, where we had a linear combination of these three terms, x, e to the x, and sine of 2x. That's what a linear combination is, just any series of addition and multiplication. That includes adding negatives and multiplying negatives. And so yeah, that was example 2, and a little note here to make this method a little more logical.